Alright, let's do some real work in one of these videos for once. I know it's usually just me messing around troubleshooting, but today we actually have to replace these float switches. I came out on call in the middle of the night the other night and found that they were bad, or at least a few of them are. Cables come up into this stainless steel box, which is definitely not explosion proof, but that is not my problem, at least not for now. And that will be a major theme in this video, because when you're working on old equipment, you kind of have to decide how good of a job you want to do. I mean, you can always tell yourself you're going to do the best job possible, but eventually time and money becomes a factor, and the fact that you're not redoing the whole thing, so it's kind of like putting lipstick on a pig. But we gotta at least do a solidly medium grade job because we have respect for ourselves. At least sometimes we do. As is standard in these places, we got some spare parts in the bottom of our cabinet, and we actually have some drawings, which is pretty cool. This is a 2-pump station with a lead and lag system. There's our new float system, revised in 1991. And no, I was not born yet at that point. There's our start and our stop floats for our lead and our lag system. Goes to these relay CR1A and CR2A. And those are latching circuits where the relay latches itself in around the start float to give you a pumping range and doesn't stop until the stop float drops out. And then there's contacts from those relays going to this alternating relay, which decides which pump is lead and which pump is lag and alternates each time the lead system stops. Then we have a transfer float and a low level float. The transfer float transfers to the secondary system, which is this float system. The floats are secondary and there's a bubbler for primary. And the low level will also transfer the system to secondary. And speaking of the low level float, it goes to that relay that I just swapped out. And I swapped it out because if the low level float is not made, neither system will work because it thinks the pump's pumped too far. So I put that relay in and I latched it closed. That way we don't have to worry about it while we disconnect all of our float wires. Everything will keep running in primary. At least that's the idea. Now that the float wires are disconnected inside the cabinet, we can go outside and start disconnecting them outside because they no longer have 120 volts on them. These were pretty spicy floats. They all had 120 on them, or at least all but one. Here, I was feeling like a strong boy. I thought I was going to pull them all out of there at once, and that did not work. So I untaped everything, hooked the pull string to a single float, and started pulling them one at a time. My tape got a little possessed, but that's all right. As you can probably tell from the title of the video, if you can read, we are not replacing these floats with more floats. We are going to replace them with a submersible transducer. We've been doing that at a lot of these stations because it's not 1991 anymore, and floats are not very reliable, and they're just giant freaking rag traps, to be honest. Anyway, we got to get these pieces of THHN out of here. There is a seal off, but thankfully someone already chipped out the Chico and replaced it with duct seal. That was not me. I know that's not proper, but I am grateful that they did that because it's a hell of a lot better than chipping Chico out of a seal off, which is basically concrete. Now that we got all the wires pretty well removed, we're going to go ahead and get the actual floats themselves out of the well. They're all attached to this pole that we call a float mast, and we're just going to unbolt everything and pull it out. Which is a hell of a lot easier said than done because the thing weighed about 10 tons with all the rags stuck to the bottom, and I couldn't get it out myself. So I spent about 20 minutes pulling rags off the bottom manually and trying to lighten it. So the next time you flush your shitty flushable wipes down the toilet, just know I'm in the sewer somewhere trying to remove them with a boat hook.
I missed the part where that's my problem.
Anyway, I'll calm down, live your life, I don't care what you do. It's my job, I signed up for it. So now that I lightened up the mast, I was able to finally get it out. Just so you know, I know people are going to comment, I did have all the safety stuff here. I had to move it in order to get the mast out, and I didn't put it in the video because I know everyone's going to criticize the setup. But I had everything, I had the tripod, gas detector blower, all that good stuff. Everything for the confined space, including a crew of people. So get out of here, OSHA. Go bother someone else. Anyway, you can see how absolutely lovely this mast was when I finally pulled it out. A lot of times I will just cut these into pieces and throw the entire thing away, but in this case I did not have a new mast. And since I still need a mast for a single float, I went ahead and cleaned it up, which is not for the faint of heart. And if anyone's wondering what this smells like, just imagine you farted into someone else's butthole and then they died, and then it came out like 6 months later.
You're super gross, man.
That's pretty accurate. So here I saved the high level float for last because it is actually going to get replaced and it will be the only float on the mast. It is a normally closed float because it's a supervisory circuit straight back to a SCADA system. So that will be the only float there, and we're replacing it because we actually do have one. And since we have the mast out, it's a good time to do it, even though the old one probably still worked. We'll go ahead and slide her back in. So these masts are made of 3/4 inch rigid galvanized steel pipe inside of Schedule 80 1-inch PVC and capped off at both ends. So they're pretty durable. So there's the float mast back in with a single float, all zip tied up and pretty. Now we can start working on installing our transducer. We pick a good spot in the well that is accessible and we drill a hole, and then we drill another hole because we hit rebar. Go ahead and insert a 1/2 inch stud anchor. Everything I'm using is 316 stainless steel for the most part, so every time you hear me say stainless steel, it's pretty much 316 stainless steel. We'll go ahead and tighten our anchor bolt down, and then we're going to add another nut and an eye nut. And the eye nut is what is actually going to hold the transducer cable. Get that nice and tight. So the way you're going to see me hang this transducer is a way I came up with a few years back, and we've had pretty good luck with it. And the people I'm doing this for have also had pretty good luck with it, so we always do it the same way when we're working here. In this installation, the transducer is just going to hang freely in the well. So the electrical cable on the transducer, the black cable, is actually rated for about 200 pounds, but we always add a stainless steel cable to get our weight rating to up around 500 pounds, which is a lot of rags, but we can definitely achieve that, trust me. So we install a threaded coupling hooked to a threaded piece of pipe, and that piece of pipe has basically a U-bolt welded to the other end, and that's what our stainless steel cable actually connects to, that U-bolt. Get everything nice and tight, and the bottom portion of the transducer is pretty much ready to go. Here's our transducer, there's the model number. It is a 0 to 15 PSI, which is more than enough for what we're doing. The stainless steel pipe obviously isn't completely necessary. I could get a hook that threads directly onto the transducer, but it adds a little weight which helps keep it down and keep it from floating, and it also kind of acts as like a spear when you pull it up through the grease. So we always just have these custom little pendants made, and we've been using them ever since. I make up all the stainless cables with crimp connectors and all my proper fittings, and I use heat shrink to kind of keep it from catching any more rags than it needs to, even though the bottom of the transducer is obviously going to catch rags. And from there, the electrical cable just gets zip tied in whatever increment I feel like that day, all the way up the stainless cable until the top. And at the top, we have a 2-foot piece of chain hanging there, and that chain is so we can adjust the transducer up and down in about 1-inch increments. So we'll start in the middle, and then that gives us plenty of adjustment just in case something changes or we mess up. Which is impossible, of course.
Of course!
Another advantage of having a separate set length cable to take the weight is when you replace the transducer one day, the cable doesn't change. The electrical cable will change, the transducer will change, but the actual stainless cable will not change length, therefore you don't have to remeasure anything. Speaking of measuring, it's time for us to measure. There's the diaphragm where the transducer actually senses the pressure, and from there we're going to measure up an amount that is achievable by the primary system. In this case, that's a bubbler. We're trying to match the bubbler. So we picked 40 inches because that's well within the operating range of the bubbler. So then we're going to go downstairs. Well, they're not really stairs. We're going to go into this confined space where the bubbler is located, and we're going to check the level down there. So we're going to wait for it to be at a level that gives us time to go back up the ladder, back into the well, and drop the transducer down until that little piece of tape hits the top of the water. Looks like someone did laundry. This is also made much easier with multiple people, and you can also skip all of this and just hook the transducer up electrically to a display and match the two displays as you drop it in. We're going to go ahead and cut our stainless steel cable where we marked it and get it crimped the same way as we crimped the bottom at the proper height, or at least close. Luckily we have our chain, so if we need to adjust up and down, we can. So that's the transducer hung. That's pretty much done. Got the carabiner just in case we want to remove it. Easy peasy. Besides any fine adjustments, that should be the wet well portion of this job done. So sad. There's our new float wire and our transducer wire going into that wonderfully deburred pipe. We're just going to have to deal with that for now because we're not replacing that today. Now we can finally start modifying the controls. We're going to put a piece of DIN rail down there, and at the top right we want to leave some room because on the door we're going to have a display, and it's pretty deep, so you want to make sure there's nothing behind it. Oftentimes we will have these setups pre-built and ready to just screw onto the back plate, but in this case I did not, so we did everything in the field, live action.
Do it live! I'll write it and we'll do it live!
So just in case you don't remember what a transducer does, or at least a submersible level transducer, all it is basically a pressure sensor, a submersible pressure sensor. The deeper in the water it goes, the higher the pressure is. Just like when you dive underwater in a pool, the deeper you go, the more water is above you and pressing down on you, so the higher the pressure is. Of course, in this case, it's like the world's worst pool that can give you HIV and stuff, but anyway, it's just sensing pressure and it's converting that pressure into an electrical signal. This transducer is taking 0 to 15 psi, converting it to 4 to 20 milliamps, and then we are going to use our controller to convert that to 0 to 415 inches, or right around there. It's about 27.7 inches of water column per psi, so that's how you do that math. There are many different styles and brands and pressure ranges of transducer, but it doesn't really matter what you use as long as you know what your ratings are. So even if I replace this in the future, I could use a different brand. As long as I get another 0 to 15 psi transducer, I won't really have to change hardly anything. But even if I do get a different pressure range, I just have to change the scaling. Alright, back to wiring. So these are all the wires that are going to go up to my door. I pre-label them and I crimp over the ends so the label doesn't fall off. And I kind of make a big bundle so I can do them all at once. I find that makes it easier. Here's the display that's going to go in the door. I am a big fan of Precision Digital. I think they're very easy to use, very easy to configure, and they seem pretty reliable. So I'm going to go ahead and cut the hole for that. My preferred tool is an angle grinder because I'm not a wuss and I know how to use tools. But I mean, some people like to hack away with a jigsaw. I mean, whatever you like. Just be yourself. Plus, I was in a room with a diesel tank, so, live life on the edge. Always deburr your hole, and look at that fit. My God, he's a professional. So this display is not only just a display, obviously, it is also a controller. It is configurable, it has 4 relay outputs, and obviously a milliamp input, which is where our transducer is going to wire into. So this is really what's replacing our floats in terms of actual electrical contacts. So here I am getting my door ready, trying to make everything even. I like to use this wire loom and heat shrink. I think it ends up looking really clean. But I will say, if you go this route, you better not be adding another wire because you are absolutely screwed. So just don't suck. I mean, what can I say? You got one shot. You got to take it. Now that all our zip ties are nice and cut with flush cutters, we can start wiring our actual display. I am using Twisted Pair shielded 16 gauge wire for the milliamp signal, I believe, and the rest is just MTW. Can use THHN, but it's a much bigger pain. Here I had to add a jumper, and I wanted to show you guys if you have to jump across terminal blocks with a jumper, that's how Phoenix Contact recommends you do it, and you're supposed to put these little Sharpie marks to indicate that you broke the middle out. Now that the electrical portion is pretty well wired up, we can pull our transducer cable in, and it's going to go up to our surge suppressor, which is that little module on the right. That is a milliamp surge suppressor. And I'll install my moisture prevention for the transducer vent tube. That vent tube just lets the transducer know what atmospheric pressure is so that it can automatically adjust, and we don't want water getting down in there. Now we can configure our display. I'm going to do this with the laptop, but you can absolutely do this with the buttons on the front. It just takes a little bit longer in my opinion. And the software is built into the display, so you don't even need to download anything. You just plug it in and it should bring it up. Our input type is current or milliamp because that is what we're working with. Our units are going to be inches. You could obviously make this feet or whatever you feel like doing the math to display. We don't have any analog output. We don't really need to mess with anything else there. Here we're going to do our scaling, but always do your decimal point first with these displays. If you don't, you'll have to redo the scaling. It's kind of a pain. That's going to be 0 to 415 inches like I mentioned earlier. I know that's not exact, but it's good enough for poop. Then we can go up and start configuring our relays. So our relay 1 is our low level, which was a single float. So the action is going to be auto, which just means it goes on and off as the level reaches whatever you set it to. So the set and reset will be the same in that row because there is no pumping range with a single float. In terms of relay 2 and 3, that is our lead and lag system, and we are going from 2 floats to a single relay. And we're able to do that because the precision digital can latch itself in, just like that latching circuit. And that is how we get our auto with manual reset, and that is why we have a set and a reset. Our set is our start, and our reset is our stop, and that gives us an actual pumping range. That is what our CR1A and our CR2A used to do. Their whole purpose was to latch in and give you a range. We are getting rid of that and just going straight to the alternator with our precision digital relay. In terms of relay 4, that is our transfer relay, and that used to also be a single float, so it's going to act the same as relay 1 and the low level. It's the same idea, it's just a single float, so we do not need that set and reset, we just need on and off. I also added a time delay to relay 3. I actually added this later, I forgot to do that. That is the lag relay, and I want a time delay so that if the power ever cycles, both pumps don't turn on at the exact same time and trip the main breaker, because at some stations that's an issue. Then we're going to send our meter data and make sure it worked. Looks like it did because the display is reading in inches instead of whatever the default was, so we definitely made a successful change. We'll go ahead and unplug our laptop and then turn our power on. This will power up the display with 120 and the power supply for the milliamp loop. We'll also slap in our 100 milliamp fuse, and now we have a level. It's like magic. These displays also have little indicator lights when the relays turn on. That's what I'm pointing to there. And since that relay 1 or low level relay is now made, I can unlatch that relay and everything should now run normally. So if we look back at our diagram, I'm just showing you here all the things that got modified or removed. Obviously all the floats were removed, CR1 and 2A were also removed because we no longer need them, and those contacts going to the alternator were replaced with the contacts from the display. The transfer and low level float were also removed and replaced with contacts from the display, just like the lead and lag. So we went from 6 floats to a single transducer and a display with 4 relays, so definitely simplified things. Here is my modified diagram. As you can see, I broke out the ruler for this one. Definitely could have been better, but most people wouldn't have done this at all, so it's better than that. So I added a 3 amp breaker on the 120 side, and that just kind of isolates all the new wiring, and it feeds the display and the power supply. This is obviously a 120 volt display, but you can get them in different voltages. And from the display, here is 2 of the relays, the lead and the lag relay from the display, and that replaced our CR2A and CR1A. We also changed what wire fed those 2 relays because we don't want to give them constant power. We came off of this wire 22, which is part of the secondary circuit. It comes off that transfer relay, which latches in when you transfer to secondary. We don't want to give it constant power because then the 2 systems would conflict with each other. So you got to make sure you use the right part of the circuit. So from there, it just goes into our alternator, business as usual. And then we have our other 2 contacts, our low level contact and our transfer contact, which, as I said before, pretty straightforward, just replacing 1 float with 1 relay. Then up here, I drew our milliamp loop, and it of course starts with a 24 volt power supply, goes into a 100 milliamp fuse, into our surge suppressor, out to our transducer in the well, and then back up to our display, and then back down to the power supply as the negative. So I always call it a loop, but it's obviously like any circuit. You have to have your power out and your return, and you have to complete that entire circuit for it to work. So this precision digital is actually capable of powering the milliamp loop. You don't have to use a separate power supply, but we oftentimes do because it gives you a little bit more redundancy, and in some ways it helps you troubleshoot things. Same goes for the fuse and the surge suppressor. They're not completely necessary, but it just adds redundancy. It's always nice to have a fuse because you can just remove it and isolate the circuit if you want to work on something, because you can short out these milliamp loops and burn something up. So always good to be able to isolate. So there you go. There's the old and the new diagram. Obviously I could have rewritten all of this in CAD, but that would have taken a lot of time. And look at that, revised 1991 and then 2025. Good God, these places need upgrades. So now we'll just tidy up the old float junction box, which is still a float junction box. It just only has 1 float instead of 7. And it's just that high well, which is only 24 volts. There's the old box, there's the new. Good God, that's beautiful.
It's beautiful.
That's the outside completely done. Then we'll move inside and add a couple stickers. Everybody loves stickers. And we even cleaned up the bottom of the old cabinet because we are just layering the lipstick on this pig. There's our little moisture prevention, little accordion thing. and our surge suppressor, our fuse, our power supply, our terminal blocks, and our circuit breakers. A little bit better, closer up look. And then we have everything going up to our door. I definitely could have made this a little bit neater, but my mentality is, as long as it's the best looking thing in the cabinet, you did a pretty good job. So it turned out okay. And that's that installation done. I know this video was a little long-winded, and I'm sorry if it was boring as hell, but hopefully you learned something, or hopefully you at least fell asleep to the sound of my boring, droning voice. All in all, happy with how it turned out, and it should last for years to come. Alright, see you on the next one.